Hi, I'm Naveen V, final year student of BTech in Petroleum Engineering, Pandit Deendayal Petroleum University, Gandhinagar. The topic of my project is model reduction of drill string dynamics to mitigate stick slip during drilling. I would like to thank Professor Nishant Parikh for providing motivation and assistance at all instants. The technique used here is hardware and loop. Hardware and loop simulation is a technique that is used in development and test of complex embedded systems. This is practiced because of the complexity of the system, safety consideration and restriction, as well as the economic factors. Here we try to implement this technique on drill string used for drilling in petroleum industries, for the above said reasons, in which safety and economic factors dominate. First part of this attempt would be model reduction, in which order of the states are reduced so that the control strategy can be applied. Among various model reduction techniques, balancing empirical Gramian method is used in this attempt. Controllability and observability Gramians are found using diaphragm equations. Their Kolsky products or Kolsky factors of the lower triangle matrix are obtained for the controllability and observability Gramians. Their product is again decomposed using singular value decomposition. The diagonal matrix of this decomposition is used to describe the dominance of the dynamics. These are known as Henkel values. Higher the value, higher the dominance of that state in the complete model. In case of model reduction, we consider a single order reduction of magnitude of the Henkel values consecutively. The transform system are obtained by using the equations a bar, b bar and c bar and using the balancing transformation T and T inverse. This transform system and the original system are same, which can be identified by the eigenvalues of A matrices of the both system. Their values remain equal. To implement this technique in drill string, to have an introduction about drilling in petroleum industry, drilling is carried out by the bit, which is the cutting tool that has an interaction between the rock, which is connected by drill collars, which is a bottom hole assembly, which is heavier than the drill pipes. This is usually heavier than drill pipe to maintain pendulum effect for maintaining vertical geometry of the hole. Stick slip is a phenomena in which the drill bit sticks and slips cyclically. During stick phase, because of the frictional factor between the bit and the rock, the angular velocity of bit is 0 and the torque which is provided by the top drive system is stored as a potential energy within the drill string. When this potential energy overcomes the frictional force, the angular velocity of the bit is up to 6 times the angular velocity that is provided by the top drive system. To study and mitigate this problem, we have to emulate the complete drill string using inertias as shown in the figure. Each inertia represents each drill string and there can be n order model of states. When we consider 6 order model, these are the governing equations. These three inertias represent the drill string, drill collar and bit. The lower one is always the bit because it shows the interaction between the bit and the rock. This is the LabVIEW code which is created by me to implement this process on the 6th order system. Here are some responses from the system. After the transformation is for the response for the step response for the system of the original and the transform system overrides each other, which shows that both the systems are equal. Based on the Henkel's values, we consider a scalar system of the transformed model and compare it with the original system. We can see there are inbuilt errors at different places. In the third graph, second order model of the transform system is compared with the original system and can be seen it better matches than the scalar model, but still there are some inbuilt error throughout the response. And we, going with the same logic, we consider a fourth state order model of the transform system and compare it with the original system, in which we can see there is a quite good match between them. So the conclusion that can be drawn from this is that the original system, which is of 6th order, can be well represented by 4th order through the transformation of the system, but still having all the dynamics intact. Before we move to the actual case, let us see the simulation. The K values which are shown here are the stiffness coefficient, D represents the internal damping coefficient, UV represents the friction coefficient of bit, U represents the well friction coefficient, which will come into play uh, during the contact of drill pipe with the valve. J represents the inertia of the string. As can be seen here, these are the A, B, C matrices of the state space model. The matrices are 0 in this system as well as in the transform system. W and WC are the observability and controllability gradients which are obtained from the Lyapunov equations. LC and LO are the lower triangle matrices of the Kolsky factor. Based on their products, we obtain the singular value decomposition in which U, V and S matrices are obtained. We can observe these are the Henkel's values, diagonal matrix. Here we can see in the scalar, from scalar to second order model, there is one order of decrease in magnitude. Similarly, there is a decrease in one order from third to fourth. So we consider scalar model, second order and fourth order model of the transform system. From these factorization, balancing transformation, T and T inverses are found, through which we get A bar, B bar and C bar matrices. Here is the waveform chart which is obtained for the original system for a step response from 0 to 7, which is run half time and then whose values changes to 10 during rest of the time. To have a clear picture of the simulation, I run the simulation again to see the chart properly. Here the frictional factor between the bit and rock is not considered. Going back to the actual drill string, we consider 1200 meter drill string, and considering the length of a triplet as 90 meter, there would be 35 drill pipes that are required and 7 drill collars, which gives us 86 order state space model, which is quite complicated and which is very difficult to implement any control strategy. These are the governing equations. Drill pipes from governing equations from 1 to 35 represents the drill string. The rest represents the bottom hole assembly, which contains the drill collar and bit, and these are the states which we need to control stick slip, which shows the velocity transmission from one string to the other. Here is the original system of 86 order. Here a nonlinear friction is considered. Nonlinear function of friction is considered to be acting at the bit. So the stick slip can be clearly observed here. During a step response, the angular velocity of the bit increases and remains constant for a while, during which the potential energy of the drill string is increasing, the torsional energy is being increased, and once that overcomes the frictional force, again the velocity of drill bit increases, and this phase is continued. This is known as stick slip, and it is maintained after a particular time. Our motto is to mitigate this. By using the same model detection technique which was discussed earlier, we get the Henkel's values for the original system and see that the reduced order model should be of 8th order, 16th order, 20th order and 24th order. And there are some decreases in the order of magnitude further also, but these dynamics are neglected because these are the dynamics that least affect the complete system, which can be seen from the pole zero diagram of the system, in which these parameters which are close to the real axis represents that their states dominate the system, and the other states which are spread throughout are least affecting the dynamics of the system. Here is the comparison between the original system and all the reduced order models. The green graph here shows the step response of the 8th order model obtained from the original system. Clearly states that this cannot withstand the withstand and consider all the dynamics of the system. Whereas when we consider other plots, they try to overlap each other, out of which 20th order and 24th order match the system more closely than 16th order. So as the order of the reduced system increases, it is more closer to the original value. But still, 24th order is much lesser than the 86th order model of the original system, and MPC can be implemented on 24th order model rather than 86th order model. Way forward for this technique is that drill string problems can be addressed by implementing controllers over it. To mitigate stick slip, a reduced order model will be very useful and easier to implement model predictive controllers and any other controller technologies, because implementation of controller on 86 order model or so requires high computational powers of the system and takes so much of time. And since the reduced order model can capture all the dominant dynamics of the system, there is no need of wasting the time and source of energy to implement the same on the higher order of model. By mitigating stick slip, we bring down the rig time and cost. We can reduce the time taken to drill level. Problems like drill string breakup are mitigated, which consumes lots of uh, cost in the complete process. This will help us increase the efficiency of exploration and reduce the complete cost for drilling each well, whose impact can be felt in the price of consumer products like gasoline, diesel, and other petrochemical products. These are the major references that are used to implement. The LabVIEW code was independently prepared with help from the professor. Thanks for listening.